Hello everyone. Let's look at another example of an inductively defined data type in Agda. My first plan was to use vectors, but you've probably seen enough of vectors already and are quite tired of them, so I thought we would look at something more interesting. And I came up with this example of derivability in a logical system. So we've already used the logical system, but now we can see how to actually represent it inside Agda so that we can reason about the logic itself in Agda. So I've defined this in a few different steps. So the first step is to define a type of the formulas of the logical system. So I'm going to keep this quite simple. I'm going to say that I have atomic formulas and I'm going to label them with a string. And I'm going to have implication between formulas. So one formula implies another one. So these are the basic syntactic structures that we're working with. And in order to talk about derivability of proofs of formulas, we need to have a notion of a context. So I'm saying that a context is either empty, it's this one, or I have a given context and I extend it with an assumption which I label with a formula. So if I assume that P implies Q is true, then that's the formula I stick here. And if I do that, I have a context and a new formula which I'm assuming, then I get a new context. So you see that this is exactly like a list, except that we like to write the new entries on the right rather than on the left. Right, so we write the context first and new things happen at the end. And this little symbol here you get by doing \c dot. Okay, and this is the actual proof system. So we are saying when a formula derives when a context derives a formula, and this symbol here you get it by typing \v-, and we usually pronounce it turnstile. And this is how we encode the proof rules of the system. So we have 4 different rules which correspond to 4 different constructors. The first one says that if you have A as an assumption in your context, then you can use this hypothesis, that's what HIP stands for, to derive A, right? So this says that A derives A, and it's fine to have more assumptions in your context if you want. This one is called weakening, or weak, and it says that if gamma already derives A, then we can weaken gamma and stick another irrelevant assumption on top of it, and we can still derive A. So this is how we move past hypotheses that aren't necessarily at the very end. We can just weaken until we get to the one we want and then do it. We have 2 more. The first one explains how to derive an implication. And it says for gamma to derive A implies B, it is enough for to derive B after you've assumed that you know A. Right? And up goes the other way around. It says that if gamma derives A implies B, and if gamma derives A, then we get that gamma derives B. So this is like the application of a function to an argument, or the modus ponens rule of logic if you want. Okay, so let's look at some example derivations. So here I would like to show that A derives A. Okay, so how do I do that? Well, I have to use one of these constructors, and we see that this exactly matches the first constructor, which says that I have a hypothesis that A is true, and now I want to show that A is true, and this is the final thing in my context, so I can just use HIP immediately on this. So that's easy. Here's a slightly more involved example where I assume that A is true, and I assume that A arrow B is true, and I would like to derive that B is true. So that's also quite simple, right? So you're just going to be the application. So it's going to be an application of something to something. Okay. And then this is now yellow because Agda doesn't yet know what I want to apply to what. And in particular, Agda can figure out that the final thing is going to be B, but it's not clear what this thing that I'm applying it from is going to be, right? But I know that this is going to be this assumption, which is my most recent one. So that's my most recent hypothesis. And now I just figured out everything. There's no more yellow. And here I need a derivation of A, which I have here. So that's not my most recent one, so I can't use HIP immediately. But if I use beacon, then that means that I get to peel off the outermost thing and do it in this smaller context. And now here it's HIP. Right. Okay, so that's how we actually construct derivations in this system. So we see that it's a bit cumbersome. It's not something you would actually want to use yourself. You would want to have some kind of parser support for doing this or something. But it's, as we will see, it's very convenient for proving things about the system. Okay, so what have we learned? We have learned that we can use inductive families, which is a fancy word for data, where we're not just defining a set, but a family of things, to encode things like derivability and, in general, other tree-like structures. Right? Things are built up from below, right? So if you think of these things as proofs, then a proof is a finite tree of all the different applications and abstractions and weakenings, etc. And it's easy to show what is derivable because you just derive it. But as a bit of a cliffhanger for the next video, how do you show that something is not derivable in this system?